Okay, good evening, everybody. Hey, I'm excited to share what I've learned about totient, modular arithmetic, congruences with you on tonight's video. I saw this on Dr. Michael Penn's channel, which is the wildly popular mathematics channel, where he's interested in all kinds of things, but number theory is one of his favorites, it appears. Now, let's go ahead and get to the problem because I was stunned that you could actually even answer a question like this. So he reveals to us that 2 raised to the 29th power is a 9-digit number. And of course, I guess you need to use a calculator to determine that. That's cool, but 2 to the 29th is a 9-digit number. But the thing that makes it a little more interesting and doable actually is that there's 9 distinct digits. Okay, well, there's 10 digits. 0 to 9 is 10 digits. So there's clearly going to be a digit missing in this 9-digit number. And again, there's no repetitions. It's 9 distinct digits. And you can use number theory and other things, it turns out, to find out what the missing digit is. And of course, it's cheating to use calculators or technology. But now, it took me a while to even understand the question, but I realized partially from Dr. Penn's tool here that any number is going to be congruent to the sum of its digits, mod 9. I actually proved that just to convince myself, but any number, a decimal number has a representation in terms of powers of 10, right? So it hit me that, look, 10 raised to the nth power is congruent to 1 mod 9. So that means a lot of stuff is going to get wiped out or replaced by 1. And you could see how the sum of the digits would just fall out of that. For example, if n is equal to 2, 100 is congruent to 1 since 100 minus 1 is a multiple of 9, namely 99. All right, so that comes in super handy. In fact, it's as far as I know, you have to use that. Although there was a guy who did this a little bit differently, and I'm going to share that with you too. But I don't want to go through all the details of this, but just as an example. Let's say that you did your reduction of 2 to the 29th modulo 9, and you got that it was congruent to 44. That would mean the last digit would have to be 1, because the sum of the digits 1 through 9, the natural numbers 1 through 9, is actually 45. Now, in a similar fashion, if you reduced 2 to the 29th modulo 9, and you got that it was congruent to 42, 3 would be the last digit, because 42 plus 3 is the only missing digit. 42 plus 3 is equal to 45. And I even went to the trouble to produce a fact about that. I realized that was good for my understanding, but it wasn't really necessary. All you really have to do is just get down to the business of satisfying the congruence 2 to the 29th and get it down to a 2-digit number in the range of the sum of the digits. Now, there's some people that didn't even know about the totient function. That's fine. I didn't know much about it either. But the totient function actually produces a tool that leads to congruence reduction. It turns out, and again, I've learned a lot about this, but just to keep the video relatively short, it turns out because of the totient function, it gives you a quick way to find out when a natural number raised to a particular power is actually congruent to 1. All right, now what this really says is that if you run into any terms, you can see that if you do exponent manipulations on 2 to the 29th, that it's possible to get it in terms of 2 to the 6th. All right, and so any power, any 2 to the 6th power could be replaced with 1, or anything raised, 2 to the 6th raised to any power would also just be 1. Modulo 9. Now, if you take a look right over here, just using the properties of exponents, you can rewrite 2 to the 29th in this fashion. But there sits 2 to the 6th, right? 2 to the 6th, but 2 to the 6th is 1, and you raise it to the 4th power, it's still 1. And so you see, that's what I mean by it's a congruence reduction tool, okay? And so we get 2 to the 29th, just like that, is congruent to 2 to the 5th, which is a manageable number. It's a tractable number to work with. 2 to the 5th turns out to be 32. 32 leaves a remainder of 5 when you divide by 9. all right? And so 41, if you think about it, it's congruent to 41. Well, the only way that could happen would be if 4 had been left out of the original 9 digits. 41 plus 4 is 45. So just like that, we see that the missing digit has to be 4. Now, I would like to say more about the Totient function. I won't right now. I have learned a little bit more about it, but this isn't the only way to fly, really. I would like to point out right here that one of the subscribers on the channel started with 8 congruent to -1, which is certainly true, mod 9. He started with that without even appealing to anything about the Totient function. But notice if 8 is congruent to -1 and you square both sides, which you can do, congruence behaves very much like equality. If you square both sides of this congruence, you get 64 is congruent to 1. But where have we seen that before? Right here. That's what the Totient actually gives us. Okay, so or this observation actually implies Euler's Totient function result. Okay, and I'm going to do another video on the Totient function. It's really interesting stuff, despite some of the commentary of some of the people that thought that Dr. Penn made the thing too hard. Now, here's I want to give credit to this guy right here. This was one of the most clever things I'd seen in a while. One of the people at the website by the name of Doug Rosengard, and I don't think he minds me sharing his name. I don't know him, but he posted his name, and he's apparently a subscriber at Dr. Penn's site. He just observed numerically that 8 is congruent to -1 mod 9. All right, 8 minus a -1 is 9, and 9 is certainly a multiple of itself, right? And he produced the following string of equality/congruences. And there is a difference between equality and congruence. Sometimes it's a little subtle, but there is a difference, even though they have a lot of the same arithmetic properties. Now, here this kind of blew me away. He had the foresight to decompose 2 to the 29th into 2 to the 27th times 2 to the 2nd. All right, and that's pretty cool, because you see what he noticed is that 2 to the 3rd would pop out of that. You see, by properties of exponents, 3 times 9 is the 27. You see right here. But look, what do we have? We have 2 to the 3rd. That's 8. All right. So notice in this next piece right here, the 2 to the 3rd. Like I say, this is kind of a congruence reduction thing that you're going through. And so all of a sudden, this whole nasty thing is just replaced with -1, and you get the 2 to the 29th as you go across is congruent to -4. Now, I know this may be kind of annoying. I like stringing the congruences together, even if it's a mile long. I just think it's better that way. Perhaps a little unreadable, but you just have equality/congruence all the way across. You're not saying anything or going down to the next line and keeping anything in your head. It's all right there in front of you. Well, -4 is also congruent to 41. In fact, it's a multiple of 9 away from 5, which I was talking about earlier. But in any event, so the very same thing happens, and for the very same reasons. This results also in the missing digit being 4. Okay, and again, parenthetically, I put 45 as the sum of the first 9 natural numbers. And I wrote out here, it happened because 8 is congruent to -1. And again, that's where Doug started. He just noticed this, and he strung this thing together without having to think about Totients or anything, like that. Even though, as I mentioned earlier, I know I sound like a broken record, 8 congruent to -1, when you square both sides, you get Euler's Totient result. So he didn't use the Totient function, but what he did was equivalent to using the Totient function without knowing what the Totient function was. Now, I think that's all I have for you, folks. And I've always wanted to say this, Alex, but this is a good time to stop.